When it comes to pushing the boundaries of science and engineering, few breakthroughs are as electrifying or as controversial as the recent development in ultra-strong steel by Chinese researchers. Imagine a material tough enough to survive the insanely harsh environment inside a nuclear fusion reactor. Sounds like something out of a sci-fi movie, right? But here's the twist. China has actually achieved it. Dubbed CHSN01, this innovative alloy boasts a strength that once seemed utterly impossible, capable of withstanding the ferocious conditions that previously shattered even the most resilient materials. It's already making waves in China's experimental fusion device, the Believe Engineered Science and Technology, BEST reactor, slated for completion by 2027. And this is just the beginning. Now, to understand why this steel is such a game-changer, let's dive into what's happening inside a fusion reactor. It's basically trying to mimic the sun, cranking temperatures into the millions of degrees Celsius to fuse atomic nuclei. To contain this searing plasma, powerful magnets are used, but these magnetic fields demand the magnets be cooled to nearly absolute zero, around minus 269 degrees Celsius, to remain superconducting. They also have to withstand magnetic forces of up to 20 Tesla, which is almost double the strength used in the largest fusion experiment in France, known as ITER. The problem? These extreme conditions are lethal to most metals, which tend to become brittle or lose their strength under such stress. Toss in a historical snag, like when ITER's cryogenic steel lost ductility during testing, and it's clear why building resilient materials for fusion reactors has long been a formidable challenge. For more than a decade, scientists around the world have been trying to crack this nut. Early efforts focused on tweaking existing alloys, adding elements like vanadium, carbon, and nitrogen to improve their abilities. While progress was made, the materials still fell short of what was needed for reliable fusion operations. The breakthrough came in 2020 when Zhao Zhongxian, a renowned cryogenic physicist and recipient of China's highest science honor, joined the effort. His expertise prompted a major rethink of the project's approach. By 2021, China had established ambitious targets, a yield strength of 1,500 megapascals and at least 25% elongation at cryogenic temperatures. Goals that would deliver both impressive strength and flexibility in the cold. Fast forward to 2023, and tests confirmed that CHSN01 could endure 20 Tesla magnetic fields and withstand stresses of 1,300 megapascals without failure. By May of that year, this steel was already being installed in the BEST reactor with hundreds of tons used specifically for its conductor jackets. And it's not just about fusion. This domestically produced steel represents a strategic leap for China, reducing dependence on imported high-grade steels and opening doors to advancements in other fields, such as particle accelerators and deep space exploration. But here's where it gets potentially controversial. Unlike ITER, which is purely for research, China's goal with the BEST reactor is to generate commercial power. That means the materials inside must be more durable and capable of handling even tougher conditions, pushing the limits of existing technology. Physicist Li Lifeng noted back in 2011 that future reactors would need magnetic fields stronger than 11.8 Tesla. With CHSN01's capabilities, China seems poised to meet and perhaps surpass these demanding specifications. So, the question is, will this steel revolutionize fusion energy and related industries? Or are we rushing into a future where the hype outpaces real-world practicality? Could other nations follow China's lead or see this as a threat? Drop your thoughts and opinions in the comments. This breakthrough isn't just a step forward. It might just redefine the entire landscape of energy research.